Okay, last time, if you remember, we were talking about the reactions of aldehydes and ketones, and we had gone through some examples of just the negative nucleophiles reacting with the aldehyde or ketone, which always went through that tetrahedral intermediate. And then we protonated what was the carbonyl oxygen, and we ended up with the addition product, which was the alcohol. All of them worked with basically the same mechanism. And then we ended lecture last time where we talked about what would happen if it were a neutral nucleophile. And we said the main example of that we would talk about was amines. And then we looked at the fact that primary and secondary amines gave a little different product. So if you're looking at your notes from last time, we ended with that schematic where I showed primary amines give imines and secondary amines gave enamines. So they give a little different product, but mechanistically we're going to see there's only one subtle difference between them that ends up leading to a slightly different product. And so what we're going to do today, starting at the beginning of lecture, is actually go through those two mechanisms to compare them. Okay, so the first mechanism is going to be imine formation. And in the imine formation, remember what we're going to be doing is reacting our ketone or aldehyde with a primary amine. So I'm just going to start with a generic ketone like acetone, okay? And I'm going to react it with a primary amine. And I'm just going to use an R group. Doesn't matter what the R group is. What matters is that it's a primary amine, okay? And so from our experience, we can already kind of see what's happening. Now, what kind of, they're the two factors we always talk about here, and I think I mentioned them last time, but we will again. I've already indicated here with these arrows that this is reversible. Since the amine is going on as a neutral nucleophile and it's going to end up, as we're going to see, with a plus charge, it can easily come right back off because it's, it ends up being a neutral leaving group, so that's going to be stable. So it is reversible. But it's also going to be acid catalyzed, but in a little different way than we've seen thus far. Because this amine is nucleophilic enough, as is, to react with the electrophilic carbon of the carbonyl and break this pi bond, moving the electrons out to the oxygen, forming this tetrahedral intermediate that we've been forming in all these reactions. And so basically that intermediate is going to look like this. Here are the two R groups that were on the ketone. I've moved the electrons from this pi bond out to this oxygen, and what I've added, right, is the amine, but I've added it with the two hydrogens still on it, therefore it has a plus charge. Okay, and so as I was saying a minute ago, this is why it's reversible, because you can easily see that these electrons could come back in and just kick off that amine group, and it would come back as a stable amine. So there is the reversible reaction, but it does proceed as written, because what happens here is a proton transfer. And we kind of foreshadowed on this in the last lecture. You get a proton transfer. What's going to happen? You're going to have a proton from this nitrogen transferred to the oxygen. Now, is that happening in an intramolecular way in the same molecule, or is it between two different molecules? Either way, proton is transferred. So that means that I'll end up protonating that oxygen and deprotonating the amine. So I end up with this intermediate, which is called a carbonyl amine. Okay? And it's not a charged species, carbonyl amine. It is at that point that the acid catalysis comes in and comes into play. This carbonyl amine interacts with aqueous acid. Okay, and when it does that, we've done this enough. What happens when you put an alcohol in the presence of an acid? We see this all the time. The OH takes the acidic proton, all right, and ends up being protonated. So we would go through this intermediate now, where I've protonated the hydroxy group, right, and I still have my amine that has added, okay? And then what happens next? Well, what happens typically when we protonate an OH? We make it a better leaving group. That is water now. Very good leaving group. So basically what happens is the lone pair on this nitrogen comes in to form a double bond. And when it does, it kicks off water as the leaving group. And therefore the result of that, and I'm going to write on this arrow, and the reason I'm doing this is I'm emphasizing the fact when we talked about this mechanism in a general sense, we said the thing that made the neutral nucleophile like amine reacting with a ketone or aldehyde, it had a different result because you were expelling water. And this is the point where water is expelled. And remember what happens then is that we're forming a double bond. I'm going to draw it like this. We're forming a double bond between what was the nucleophile coming in, right, and the carbonyl carbon. And then this still has the two R groups attached. And so my nucleophile has kind of just replaced the carbonyl oxygen. So now instead of the oxygen here, we have the nitrogen. And in this form, it still has a plus charge because it still has that proton on it. I moved these electrons in when it was neutral, so it now has a plus charge. Okay, so now what's going to happen? Well, I've expelled water. So I have a water present here. The water comes in, takes off this proton, moves those electrons in. And so in the magic of digital lectures, I can erase this because I know that you're able to pause it and make sure you got all that down, because the result of what I just showed is that you would form this product, which is the imine, because I've lost that proton from the nitrogen. And notice again how, when you started with the ketone, you had these two R groups and it was C double bond O. Now all that's happened is the nucleophile has replaced that. But I've also formed H3O plus, which means that it's catalytic in acid from that carbonyl amine to this result. Now, if I can say something here, you might, if you did any research into my research, you'll see that imines are something that are important to me. And I really love this mechanism that we just went over. I think it's really slick and kind of cool. Hint for future reference. All right, so that's how imine formation works. And you can see that it's clearly like we talked about, where when a neutral nucleophile adds to a ketone or aldehyde, we expel water and we end up with this double bond between the nucleophile and that carbonyl carbon. I keep emphasizing that just to make sure that that's all understood. Now, there is something interesting about the acid catalysis in this reaction. It's not. It has nothing to do with the reactant, the nucleophile or the carbonyl compound. Usually we see acid catalysis as making the carbonyl more electrophilic. That's not how it's happening here. This is a little different than those other cases. And it turns out that there is a maximum reaction at a certain pH. So this reaction is not only acid catalyzed, but it's sensitive to exactly what the pH of the reaction is. And so you can do a little experiment where you do pH versus rate for this reaction. And the reason I like to show this is it kind of explains the subtleties of catalysis in terms of acid and base. And so if I do a reaction energy profile for imine formation, where I plot the rate of the reaction against the pH, okay? Rate of the reaction versus pH. And so on my scale down here, let's put 1, 2, 3, 4, 5, 6, 7. I mean, we could go all the way to 8. So we're really looking at what the acidic end of the pH scale. And if we did this reaction at all of these different pHs and recorded the rate, what we'd see is there would be a curve like this, where the maximum rate would be at about 4.5 on the pH scale. Okay? And so if you were doing this reaction, you'd aim for having a pH of about 4.5. Now, why would this make sense? I mean, this is experimental result, so we know that, in fact, that is where the reaction rate is the highest. But why would that be? When you're at this range of low pH, you notice that the reaction is very slow. The reason for that is your amine starting material. When you're at low pH, it gets protonated. You end up with a protonated amine because you're acidic enough for this to act as a base and be protonated. Once you've done this, this is not nucleophilic anymore. And if it's not nucleophilic, it can't react with the carbonyl compound and lead to the imine. Okay? At the high pH range of the acidic window, so when you're in this region, and I'm going to say higher pH because I want you to understand that we're still in the acidic range, but the higher pH range for the acid, it won't protonate the carbenolamine. Remember that was the intermediate that had the OH that the acid protonated so you could expel water. Okay, so pH too low, too acidic, you protonate the nucleophile, it's not nucleophilic anymore. At the higher end of the acidic scale, it's not acidic enough to protonate your carbenolamine, so you can't expel water. So the ideal pH is right here at about 4.5. It's not acidic enough to protonate the nucleophile, but it is acidic enough to protonate the OH and the carbenolamine and allow the reaction to proceed. All right. Now, what are some examples of imine formation? And this will demonstrate exactly what you would put on your flashcard for this reaction. So if you have something, these are just examples. Say you have benzaldehyde, and I can react it with a primary amine. So all that's important is that the amine is primary. Then the R group doesn't matter. So I could, have this this amine that has the ethyl substituent as the R. And so what's going to happen? The transformation, and you have an acid catalyst. The transformation is simply to remember what you're forming is a double bond to the nucleophile. Okay, it kind of replaces the carbonyl oxygen, and this is the imine that is forming. So that's what you would see on your arrow on the reaction section of the test. Okay? Now what about if we're not using a primary amine? What if we go to the case with the secondary amine? And that gives us the N-amine product. So mechanistically it's different. So let's look at N-amine formation. Okay, in N-amine formation, we're going to see something that's very similar to imine formation. And it's got to be similar because they're both amines that are reacting, but there is just this subtle difference. And so just as you saw in the very first schematic from last lecture where I was comparing the two, draw your carbonyl compound like this. Okay? And all I'm emphasizing, it doesn't matter what's here. I'm just emphasizing this proton right here. This proton is off of an alpha carbon. And so to go through this mechanism, you need to have identified that there is, in fact, an H on this alpha carbon. Okay? And that'll become apparent soon. Okay, so I'm going to react this now with an amine, but it's going to be a secondary amine where I have two R groups, only one proton. Just like we saw with imine formation, this amine is nucleophilic enough. Doesn't involve any acid or base catalysis at this point. Okay, but this amine then acts as a nucleophile and reacts with the electrophilic carbon of the carbonyl, breaks the pi bond, moves the electrons out to that oxygen, forming the tetrahedral intermediate. All of these reactions do that. You can almost just instinctively come in here and draw your intermediate. So I've pushed the electrons up to the oxygen to form that tetrahedral intermediate. And I'm going to draw this particular intermediate like this. I'm going to draw my secondary amine in that position. And it came in as a neutral nucleophile, so it's got a plus charge, right? And that's going to leave that substituent there. Okay, just like we saw in imine formation, at this point we have proton transfer. So the good thing is these reactions are looking pretty much the same mechanistically, right? That's good. Proton transfer, again, is it intramolecular or is it inter? I don't know, but proton gets transferred. And so that means you're going to end up with your protonated carbonyl oxygen, right? And your amine substituent that's on there is now deprotonated. Okay? And I'm going to draw it a little differently at this point. Now I'll leave it like that for now. And so what happens next at this point? What happened when we had the imine formation? Same thing's going to happen here. This is where the acid comes into play. This is like the carbonyl amine. And so this OH, as we've seen a million times, when put in the presence of an acid, is going to get protonated because it's going to be converted into the protonated OH, which is a good leaving group because it leaves as water. So I'm going to draw my secondary amine out like this, the same way I did with my primary amine. Okay, and so what happened in the imine formation this last time, right? What happened? You have lone pair on this nitrogen comes in, you form a pi bond between the nitrogen and what was the carbonyl compound, carbonyl carbon, excuse me, and you expel the water. So you have that same step here where water is expelled. Okay, and the result of that then is what? The result of that is this was the carbonyl carbon. Here's your amine that's added, the secondary amine. It's got a plus charge on it now because I've moved these electrons in. And then I have my substituent that's attached to that, right? And what else do I have? The other carbon that was on there. Okay? So that's what I have. Now, by the magic of digital technology, y'all, can pause there and make sure you get everything written down. I'm just going to basically redraw this structure right at the top of the board so we can continue. So carbonyl carbon doubly bound to the nitrogen. It had two R groups on it like this and had a plus charge. And then I had my two substituents on what was the carbonyl carbon. Now, if you remember what happened with imine formation, we said we had this water present, and all we did is pull a proton off the nitrogen, right, to make it neutral, and we had our imine. So I just have to take the proton off of nitrogen. There is no proton on nitrogen. There's no proton to remove there. So I have to take off this proton. And so when I do, these electrons close in to form a double bond between this carbon, which is the alpha carbon, and the carbonyl carbon. And when it does that, it pushes these electrons back to the nitrogen. And so in this last step, which is just the deprotonation, that is the difference between imine formation and enamine formation, just this last step. Because now the double bond exists between what was the carbonyl compound and the alpha carbon. Okay, and so therefore now your nitrogen is neutral like this. And so that is what we call the enamine, because it's an amine and you have the double bond. So do you see the subtle difference is just the fact that this nitrogen does not have a proton on it. If it did, you'd have that same imine formation, but the fact that there's no proton there because we started with a secondary amine, you get the enamine formation. All right? So, another interesting mechanism, okay? But it's virtually the same as imine formation, only that subtle difference at the very end, okay? Next reaction we want to talk about is what happens when you react hydrazine as your nucleophile with a ketone or an aldehyde. Now, this was discovered at a time when they would name reactions after the people that discovered it. So this is called the Wolff-Kishner reaction. But it's a reaction of hydrazine. And hydrazine is basically, looks like two primary amines attached together, two NH2 groups. That's hydrazine. Okay? And hydrazine reacts with ketones and aldehydes to give an interesting result. Okay? This would be the kind of thing that you'd put on your flashcard, the general reaction. So what happens is if you have something like this ketone, and you react it with hydrazine in the presence of base, and it's usually potassium hydroxide, you will form this product. And I'm putting these in for emphasis. Okay? You have two hydrogens there, and in the course of the reaction, you're losing nitrogen gas, right? And you're expelling water. So the expelling water thing is kind of similar to what we just saw with imine and enamine formation, and there's a reason, because you would imagine hydrazine would have similar reactivity as enamine, right? Because it's got the NH2. The difference is this loss of nitrogen. And the result of that basically is then the reduction of that carbonyl. That's a reaction we've seen. We've seen how you can do it with hydrogen gas and catalyst. We've done it with, what else? Clemenson. We've done it several different ways, and we're going to compare those all in a minute at the very end of this. But this is a reaction that we've seen before, but the difference is, unlike the other cases, this one is base. It's under basic conditions. Clemenson was acidic. This is basic. Okay, so what's happening in this reaction? There must be a mechanistic explanation for why we end up with this reduced product through the loss of not only water, expelling water we've seen before, but now we're also expelling nitrogen gas. So how is this happening? Let's look at this mechanistically. Okay, so using just a generic ketone, let's put R and R prime here because we're going to have a lot of stuff to keep up with, and I'm going to react it with hydrazine. Now y'all are getting experienced enough with organic chemistry where I know you're able to see big picture things. If I just put this on the board and told y'all, please give me the first step, all of you sitting out there right now watching would know exactly what to do, right? This is a nucleophile. It will react with the electrophilic carbon of the carbonyl, breaking the pi bond, moving electrons out to the oxygen, forming the tetrahedral intermediate. Have you not seen how this happens every time? I mean, big picture, nucleophiles react with ketones or aldehydes. This is what they do. And so that's going to give me that tetrahedral intermediate, okay, which is going to look like, we saw before. Now, what I'm going to do right here, though, is I'm going to put a double line. Because, as you can see, this reacts exactly the same as the primary amine did, okay? And so I'm going to write down here, same as imine formation. So you're going to go through exactly the same steps until you end up with this product. And don't worry, I'm going to stop here for a minute to make sure we're all on the same page. That's a prime. I don't want to get mixed up. So basically what this means is this following the same exact mechanism, where this would have been an R group instead of an NH2, you would end up with this product which is imine-like, right? Because double bond to the nitrogen. But instead of being an R group, this is now an NH2. So it's exactly the same electron pushing all the way to this point. This would have been the final product of imine formation. All right, but in this particular reaction, it's not the last step. Okay, so I'm going to redraw this. Over here. Remember, double bond between what used to be the carbonyl carbon and the attacking nucleophile, and you've expelled water, which we saw. So this is equivalent to the imine, but now it's got that NH2 group on there. And so what's going to happen now is the difference is you have that KOH. So now I have a base that's present. Okay, that base is going to do something different. It's going to pull a proton off of this NH2, because that's where the acidic proton is. And when it does that, it's going to move electrons onto this nitrogen. So you're going to end up, and by the way, I'm still really operating in brackets here, right? And so what happens when you pull off that proton and move the electrons to the nitrogen, I end up with this intermediate, right? And then this can basically resonate X, Y, Z, right? So I'm going to draw my resonance arrow, and I'm going to draw the resonance form for that right here. So nitrogen there, double bond. All I've done is resonate this minus charge down here to the carbon, which moved this pi bond to here. You see where I am? All right. Now I'm in a situation where you're going to have water present, right? Because this OH has pulled a proton off of this, so I have water around, right? This is going to pull a proton off of water. And so that's going to lead to this. I've put a proton back on my carbon, and so I have this, and that's a bond. All right? So now what happens? Now I kind of repeat the same step again, because right here, I'm not having to go through this quite as slowly, right? Because I know you can keep replaying it. But notice that I'm doing this proton exchanges here with the water, because here I pulled a proton off, I formed water, but now this has pulled a proton off of water and I've reformed the OH. So I have this base now, and what is that base going to do? That base is going to pull off this proton, move these electrons in. And when it does that, it's going to push those electrons down to that carbon. So it's kind of the same thing we saw here, right? Kind of the same deprotonation step. So what I'm going to do through the magic of digital lectures is I'm going to erase this. And what we're going to do is we're going to start again with the result of this electron push, which is basically what? I'm going to leave that there for a second, because what I've done now is I have my R and my R prime and my H, and I have the minus charge on the carbon because the electrons have moved in when this bond broke. And when it did that, it formed nitrogen gas, right? And triple bond N. And it also formed water because that OH pulled that proton off. Okay? And so is that the product? No, because what happens is this pulls a proton off of the water, moves the electrons out. So the final result of this is where I've protonated this carbon. And so you can see this was the carbonyl carbon. And what have I effectively done? Put 2 hydrogens on it. Okay? But I've also formed the nitrogen gas. And I've also regenerated my base. Okay? That's kind of a slick mechanism, isn't it? It's kind of cool. Okay? Now, the result of that reaction, as we showed in the general sense, was the reduction of that carbonyl. Okay? And so we've talked about several different reactions that do this transformation. So let's kind of revisit that. Because we talked about the fact that we could take this particular carbonyl compound and we could treat it with hydrogen gas and a catalyst. So hydrogenation, you know, this could be palladium or platinum or whatever, and we're going to actually reduce to the alkyl substituent. So you're basically, in essence, again, putting the 2 H's there. That was one way to do it. It's just a neutral reaction. There's no acid or base. It's hydrogen gas, right, and the catalyst. Okay, but we also talked about how you could take this same ketone and treat it under Clemmensen conditions, and that was the zinc mercury, right, with acid, and you ended up again forming what? The alkyl substituent. So both of these do the same transformation, okay? But this one is acid catalyzed. This one is neutral, okay? And now we've also seen that we could take this ketone and react it with hydrazine under the Wolff-Kishner conditions, and again get the same product. So 3 different ways of doing the same thing, okay? But the conditions are different. Neutral, acidic, basic, okay? Now the other thing that's important is these 2 will reduce carbonyls anywhere on the molecule. This one only reduces carbonyls when it's benzylic. So that's another difference, and we've talked about that, right? These conditions only work to reduce this carbonyl if it's once removed from the aromatic ring. These 2 will reduce any carbonyl. And so just to emphasize that with our new reaction, what that means is if I have this ketone and react it with hydrazine, potassium hydroxide, I will in fact reduce to the alkane. It doesn't have to be benzylic. All right? How are we doing on time? We're okay. All right? So next reaction is what happens when alcohols are acting as the nucleophile. So what happens when alcohols as a nucleophile react with a ketone or an aldehyde? Okay, and they're going to form a kind of compound that we call an acetal. It's a name for kind of the functionality that forms when you react an alcohol with a ketone or aldehyde. Now this reaction is going to be a little different than what we've seen because two equivalents of alcohol are going to react. And we're going to be able to explain that mechanistically. But another important thing is we're going to see that these acetals that form are actually good protecting groups for carbonyls. So you can react a carbonyl compound with an alcohol and it forms this functionality that serves as a protecting group. So we're going to bring that principle back in. But first we want to talk about the reaction in general, because what an acetal is now known as, it's equivalent to the situation where you have a carbon that's attached to two R groups, or one R group and an H, and then two OR groups. These are the two things that are going to come from the alcohol. So that's why I'm saying you have two equivalents of alcohol that are going to add. But this is a little aside. Put your pencils down, because this is one of those things where I like to kind of go off on a rant about something. You know, the term acetal is kind of become a generic term for functionalities like this, but it's not always correct, because there's something also called a ketal. And an acetal is when this is an H. A ketal is where this is an R. I mean, that is the standard nomenclature going back to when I was, the young chemist learning this. But for some reason, ketal doesn't exist anymore. All of these are called acetals. Incorrect as hell, but that's the way it is. So we're going to call them acetals. Right? And so, in general, to make an acetal, what you do is you take your ketone and you're going to react it with two equivalents of the alcohol, and under acid conditions, and it will in fact then give the acetal. And I didn't use R, so I won't put them there. Okay, so already you can see from what I've drawn in general that this is reversible and it's acid catalyzed. So we know both those things. Okay, and so how is this going to happen mechanistically? Okay, so let's use a cyclic ketone. Let's kind of change things up. So we'll use this ketone as our example, and I'm going to react it with, let's say, methanol. Okay. Now remember, if I don't indicate one equivalent or anything else, the assumption is there's enough alcohol present to totally react. So there is excess. This is acid catalyzed. Okay? So, we're kind of going back to the sense that, this reaction is acid catalyzed, right? So we kind of know what's going to happen, right? If something is acid catalyzed, that means the carbonyl oxygen is going to first get protonated. And when it does, you're going to form this intermediate where you've protonated the carbonyl. Remember, way back when we talked about hydration of ketones and aldehydes, this is what we demonstrated with acid catalysis, because what it's done is it's made the carbonyl carbon more electrophilic. By protonating this oxygen, it's become more electronegative. And in that sense, then, I'm able to take my alcohol, in this case methanol, and listen, reacts with the electrophilic carbon of the carbonyl, breaks the bi-bond, moves the electrons out to the oxygen, forming the tetrahedral intermediate. I can say this until I'm sick of saying it, because all of these reactions are occurring the same way. There is the what would normally be the carbonyl oxygen with the minus charge, but it's already been protonated, right? And so then I've added my alcohol as a neutral nucleophile. So it's going to have a plus charge, right? And so that's the intermediate that initially forms. Now what happens? Well, I need to get rid of this H, right? So what happens is another molecule of the alcohol pulls this proton off, kicks these electrons in, and you form this first neutral intermediate. It looks like that, right? Okay. And plus, just so we know it's there, that protonated alcohol that I formed right there. Okay, this has a name. It's a hemi-acetal. Okay, hemi, partial acetal, because there's not an R group here. Okay, I've only added one equivalent of the alcohol, hemi-acetal. Okay, well now what happens? Well, now I've got this alcohol that's got a proton on it. So this oxygen, sorry, forgot I had the OH. OH comes in, it's an OH in the presence of an acidic proton. We know what happens there. You protonate the OH because when you do that, you make it a better leaving group. So I've protonated that OH. So it's got a plus charge on it. Okay, I have my OCH3 here. And I've also regenerated just a normal methanol because its proton has been removed. Okay, now these electrons come in to form a pi bond and kick off this water. Okay, now who can tell me what that resembles? The same thing happens with the imine formation and the anamine formation. This is the expelling of the water. That's what happens when a neutral nucleophile reacts with a ketone or an aldehyde. So here is my expulsion of water. And I'm going to end up forming that intermediate where I now have a double bond between what was the nucleophile, right, and what was the carbonyl oxygen. But the thing here is that that is also an oxygen because it was part of this nucleophile. That's got a plus charge. So you can see this looks exactly like the imine. And it would normally be the end result of a neutral nucleophile reacting with a ketone or an aldehyde. But in this particular case, we have a plus charge. Okay? And so what happens here now is I formed this situation where I have a reactive species because now another equivalent of alcohol now can act as a nucleophile. Oh, and look, I've basically have the same thing that I did with the protonated carbonyl at the beginning of this mechanism. This carbonyl carbon is now more electrophilic because this oxygen has a plus charge. And so it's more electronegative. So my nucleophile can react with the electrophilic carbon of the carbonyl, breaking the pi bond, moving the electrons up to the oxygen, forming the tetrahedral intermediate, which would look like this. Electrons move up to that O to remove the charge, but it's already got the methyl group on it. I've reacted it with a neutral alcohol, which means that when that nucleophilic alcohol adds, it's going to have a plus charge. All right, so is that the final product? And by the way, I don't need this bracket here. I don't know why I instinctively put it there because we've been in brackets for a while. Okay, so no bracket there. And so is this the final product? No, because I have water present, which can pull off that proton, kick these electrons in, and then I'm going to form the acetal, and in the process, I'm regenerating the acid, so it's acid catalysis. Now, you notice how I was bringing up the similarity between this and the imine formation. when we're going through these carbonyl compounds, I hope what you're seeing is these mechanisms are very, very similar. And so if you're able to identify the similarities in them, it's not like you're memorizing 14 mechanisms. They're all occurring in basically the same way. Sometimes you see some subtle differences. Subtle difference here is you have another equivalent of alcohol that reacts instead of stopping at this point. Other than that, it's the same as imine formation up to this point. And so look for those things that are common. Okay? Now, as I said, once you form this acetal has some purposes. That acetal can serve as a protecting group. Same way that we saw with TMS ethers protecting alcohol functionality. Okay? And so acetals themselves are inert to several things that can make them important as a protecting group. They're inert to bases. Okay? So once you've formed an acetal, you can throw as much base in there as you want, and nothing's going to happen. They're inert to reducing agents. And of course, that would be important because carbonyls are susceptible to reducing agents. Take a carbonyl compound and react it with a hydride reagent, it gets reduced. Well, if you convert the carbonyl to an acetal first, then it can't be reduced. Okay. Also, Grignards. If you have a carbonyl compound, or if you have a carbonyl in your compound, and you're going to use a Grignard reagent somewhere else and you want to protect the carbonyl, if you convert it to the acetal, Grignard won't affect it. And the last thing is catalytic hydrogenation. So it's inert to all these things in the transformation. So if you remember the strategy of protecting groups, what we wanted is something that was easy to put on, and we just saw it was. Throw some alcohol and acid into the reaction, make sure you form the acetal. But once it's formed, you want it to be inert to a number of different reactive conditions. And certainly that's true here. But it has to be easy to remove also. And if you notice, there's one thing that's not on this list that's pretty common. But it's acid sensitive. You can remove it very easily by treating it with an acid. Okay? And so what would be the application of an acetal as a protecting group? We've already seen this example from a while ago. Okay? And when I put it up there, you might remember. So I'm making sure I'm putting up the same example we did maybe a week or so ago. Okay, we have this compound that has both a ketone functionality and an ester functionality. And remember, we talked about doing reductions. And sodium borohydride, remember, would selectively reduce the ketone. Remember when we looked at that, we were comparing sodium borohydride and lithium aluminum hydride. Sodium borohydride only reduces the ketone, not the ester. So we said, oh, we can use sodium borohydride and selectively reduce just this carbonyl. And then we said if we used LAH, it would reduce both. Right? And then I asked the question, wouldn't it be nice if there were a way of reducing just the ester without affecting the ketone? And the answer to that is yes, we can do that using a protecting group because acetal formation occurs on ketones and aldehydes, not esters. Okay? And so what I can do is take this and convert it into the acetal. Okay, then I'll be able to reduce this with LAH and nothing will happen to this carbonyl. And then I just remove the acetal and I'm back to that carbonyl. So how would I do that? Now here's a slick little trick. When we form acetals, one neat way of doing it is having your two equivalents of OH be on the same molecule. So here I just have this, I have two hydroxy groups basically on ethane. And so that's going to behave as two equivalents of alcohol, because what's going to happen is I'm going to form this acetal. See, one equivalent of alcohol added, and then the second equivalent of alcohol added, they just happen to be connected together. So you end up forming this little cyclic acetal. That protects the ketone, because now I can reduce this with LAH followed by aqueous acid workup. And so believe it or not, what happens, the LAH reduces this, right? And so when it reduces it, what is it going to form? What's going to happen to this acetal when you do the aqueous acid workup? It's going to come off. So the workup of the reduction actually removes that. And then what is going to be the result here? The formation of the alcohol. Because remember, those esters reduce to alcohols. Okay? So this would be a way of affording the reduction of an ester in the presence of a ketone. Acetals protect the group, allow me to do my reaction on the ester, and then I remove the acetal and I get back that starting ketone functionality. Okay, let's see how we're doing on time. One quick little similar reaction, and then this will be a good place to stop, because next time we'll go into something really fun called ylide formation. But we want to talk about what happens if you use a thiol as your nucleophile. And I've already talked about the fact of using thiols. Remember back when we were talking about thiols with alcohols, and I told the story about using the thiol and the stench and clearing out all the buildings at Cornell. Well, this is another reaction that I've done before that had about the same result. But basically, as you can imagine, if you use a thiol, it's going to react in a very similar way to the alcohol. Because basically, if you take a ketone or aldehyde, and this would be what's on your flashcard, and you react it with a thiol, and what I'm going to do is that slick thing again. I'm going to put my two equivalents of thiol on the same molecule, and it's acid catalyzed. And so you can form this called a thioacetal. But it's basically the same reaction. They're adding two equivalents of the thiol, exactly the same mechanism, ending up at this acetal. Now, the reason I show you this is there is a reaction that used to be done on these thioacetals where you would then react them synthetic utility in something called Raney nickel. And Raney nickel would then basically reduce. So it had the same result as a Clemenson or a Wolff-Kishner or whatever. But the problem is Raney nickel, you can't really, I don't think you can even get it anymore. So this is kind of an archaic reaction. But I wanted to show you that thiols will react exactly like an alcohol with a ketone or an aldehyde. Okay? And so that brings us to the point where we will stop here. We have a couple more nucleophiles to talk about with ketones and aldehydes, and then we'll be able to start moving into the reactions of carboxylic acids and their derivatives. And what we'll see there, again, primarily, those are nucleophilic acyl substitution reactions, not additions like we've been looking at. But all of those derivatives fall under the category of having substitutions. All right, so I will see you next time.